Okay? This is linear algebra, lecture 11. And at the end of lecture 10, I was talking about some vector spaces, but the things in those vector spaces were not what we usually call vectors. Nevertheless, you could add them and you could multiply by numbers. So we can call them vectors. I think the example I was working with, they were matrices. So we had like a matrix space, the space of all 3 by 3 matrices. And I'd like to just pick up on that because we've been so specific about n-dimensional space here, and you really want to see that the same ideas work as long as you can add and multiply by scalars. So these new vector spaces, the example I took was the space M of all 3 by 3 matrices. Okay? I can add them, I can multiply by scalars. I can multiply 2 of them together, but I don't do that. That's not part of the vector space picture. The vector space part is just adding the matrices and multiplying by numbers. And that's fine. We stay within this space of 3 by 3 matrices. And I had some subspaces that were interesting, like the symmetric. The subspace of symmetric matrices. Symmetric 3 by 3s. Or the subspace of upper triangular 3 by 3s. Now I use the word subspace because it follows the rule. If I add 2 symmetric matrices, I'm still symmetric. If I multiply 2 symmetric matrices, is the product automatically symmetric? No. But I'm not multiplying matrices. I'm just adding, so I'm fine. This is a subspace. Similarly, if I add 2 upper triangular matrices, I'm still upper triangular. And that's a subspace. Now, I just want to take these as examples and ask, well, what's the basis for that subspace? What's the dimension of that subspace? And what's the dimension of the whole space? So there's a natural basis for all 3 by 3 matrices. And why don't we just write it down? So M, a basis for M. Again, all 3 by 3s. Okay. And then I'll just count how many members are in that basis, and I'll know the dimension. And, okay, it's going to take me a little time. In fact, what is the dimension? Any idea of what I'm coming up with next? How many numbers does it take to specify that 3 by 3 matrix? 9. 9 is the dimension I'm going to find. And the most obvious basis would be the matrix that's that matrix. And then this matrix with a 1 there. And that's 2 of them. So I put in the third one. And then onwards. And the last one maybe would end with the 1. Okay. That's like the standard basis. In fact, our space is practically the same as 9-dimensional space. It's just the 9 numbers are written in a square instead of in a column. But somehow it's different and ought to be thought of as sort of natural for itself. Because now, what about the symmetric 3 by 3s? So that's a subspace. Let's just think, what's the dimension of that subspace and what's a basis for that subspace? Okay? And I guess this question occurs to me. If I look at this subspace of symmetric 3 by 3s, well, how many of these original basis members belong to the subspace? I think only 3 of them do. This one is symmetric. This last one is symmetric. And the one in the middle with a 1 in that position, in the 2-2 position, would be symmetric. But so I've got 3 of these original 9 are symmetric. But so this is an example where. But that's not all, right? What's the dimension? Let's put the dimensions down. Dimension of M was 9. What's the dimension of, shall we call this S? Is what? What's the dimension of this? I'm sort of taking simple examples where we can spot the answer to these questions. So how many, if I have a symmetric, think of all symmetric matrices as a subspace, how many parameters do I choose in 3 by 3 symmetric matrices? 6, right. If I choose the diagonal, that's 3, and the 3 entries above the diagonal, then I know what the 3 entries below. So the dimension is 6. I guess what's the dimension of this here? Let's call this space U for upper triangular. So what's the dimension of that space of all upper triangular 3 by 3s? Again 6. Again 6. And but we haven't seen well, actually, maybe we have got a basis here for the upper triangulars. I guess 6 of these guys, 1, 2, 3, 4, and a couple more, would be upper triangular. So there's an accidental case where the big basis contains in it a basis for the subspace. But with the symmetric guy, it didn't happen. The symmetric guy, the basis, so you see what, a basis is the basis for the big space. We generally need to think it all over again to get a basis for the subspace. And then how do I get other subspaces? Well, we spoke before about the subspace, the symmetric matrices, and the upper triangular. This is symmetric and upper triangular. Okay. What's the dimension of that space? What's in that space? So if a matrix is symmetric and also upper triangular, that makes it diagonal. So this is the same as the diagonal matrices, diagonal 3 by 3s, and the dimension of this of S intersect U, right? You're okay with that symbol? That's the vectors that are in both S and U, and that's D. So S intersect U is the diagonals, and the dimension of the diagonal matrices is 3. And we've got a basis, no problem. Okay, as I write that, I think, okay, what about putting together, so this is like, this intersection is taking all the vectors that are in both, that are symmetric and also upper triangular. Now, we looked at the union. Suppose I take the matrices that are symmetric or upper triangular. Why was that no good? So why is it no why am I not interested in the union putting together those two subspaces? So these are matrices that are in S or in U, or possibly both. So the diagonals included. But what's bad about this? It's not a subspace. It's like taking, a couple of lines in the plane and stopping there. A line, so there's a three-dimensional subspace of a nine-dimensional space. Six. There's a six-dimensional subspace of a nine-dimensional space. There's another one, but they're headed in different directions. So we can't just put them together. We have to fill in. So that's what we do. To get this bigger space that I'll write with a plus sign, this is combinations of things in S and things in U. Okay, so that's the final space I'm going to introduce. I have a couple of subspaces. I can take their intersection, and now I'm interested in not their union, but their sum. So this is the intersection, and this will be their sum. So what do I need for a subspace here? I take anything in S plus anything in U. I don't just take things that are in S and pop in also separately things that are in U. This is the sum of any element of S, that is any symmetric matrix, plus any element of U. Okay, now, as long as we got an example here, tell me what we get. If I take every symmetric matrix, take all symmetric matrices and add them to all upper triangular matrices, then I've got a whole lot of matrices, and it is a subspace. And it's a vector space, and what vector space would I then have? Any idea? What matrices can I get out of a symmetric plus an upper triangular? I can get anything. I get all matrices. I get all 3 by 3s. It's worth thinking about that. It's just like stretch your mind a little, just a little, to think of these subspaces and what their intersection is and what their sum is. And now, can I give you a little, let's figure out the dimension. So what's the dimension of S plus U in this example is 9, because we got all 3 by 3s. So the original symmetric space had dimension 6, and the original upper triangular space had dimension 6. And actually, I'm seeing here a nice formula. That the dimension of S plus the dimension of U, if I have two subspaces, the dimension of one plus the dimension of the other equals the dimension of their intersection plus the dimension of their sum. 6 plus 6 is 3 plus 9. It's kind of satisfying that these natural operations, and this is it actually. This is the set of natural things to do with subspaces, that the dimensions come out in a good way. Okay, maybe I'll take just one more example of a vector space that doesn't have vectors in it. Come from differential equations. So this is one more new vector space that we'll give just a few minutes to. Suppose I have a differential equation like d second y dx squared plus y equals 0. Okay. I look at the solutions to that equation. So what are the solutions to that equation? Y equals cos x is a solution. Y equals sine x is a solution. Y equals, well, e to the ix is a solution if you allow me to put that in. Oh, but why should I put that in? It's already there. You see, I'm really looking at a null space here. I'm looking at the null space of a differential equation. That's the solution space. And describe the solution space, all solutions, to this differential equation. So the equation is y double prime plus y equals 0. Cosine's a solution, sine is a solution. Now tell me all the solutions. So I don't need e to the ix. Forget that. What are all the complete solutions? Is what? A combination of these. The complete solution is y equals some multiple of the cosine plus some multiple of the sine. That's a vector space. That's a vector space. What's the dimension of that space? What's a basis for that space? Okay, let me ask you a basis first. If I take the set of solutions to that second order differential equation, there it is, those are the solutions. What's a basis for that space? Now remember, what question am I asking? Because if you know the question I'm asking, you'll see the answer. A basis means all the guys in the space are combinations of these basis vectors. Well, this is a basis. Sine x, cos x, there is a basis. Those two, they're like the special solutions, right? We had special solutions to ax equal b. Now we've got special solutions to differential equations. Sorry, we had special solutions to ax equals 0. I misspoke. The special solutions were for the null space, just as here we're talking about the null space. Do you see that here is those two, and what's the dimension of the solution space? Is how many vectors in this basis? 2. The sine and cosine. Are those the only basis for the space? By no means. E to the ix and e to the minus ix would be another basis. Lots of bases. But you see that really what a course in linear differential equations is about is finding a basis for the solution space. The dimension of the solution space will be 2 because we have a second order equation. So that's like there's 1803 in 5 minutes of 1806 is enough to take care of 1803. Okay. So that's one more example, and of course the point of the example is these things don't look like vectors. They look like functions. But we can call them vectors because we can add them and we can multiply by constants, so we can take linear combinations. That's all we have to be allowed to do. So that's really why this idea of linear algebra and basis and dimension and so on plays a wider role than our constant discussions of m by n matrices. Okay, that's what I wanted to say about that topic. Now, Of course, the key number associated with matrices, to go back to that number, is the rank. And the rank, what do we know about the rank? Well, we know it's not bigger than m, and it's not bigger than n. So, but I'd like to have a little discussion on the rank. Maybe I'll put that here. So I'm picking up this topic of rank 1 matrices. And the reason I'm interested in rank 1 matrices is that they ought to be simple. If the rank is only 1, the matrix can't get away from us. So for example, let me create a rank 1 matrix. Okay, suppose it's 2 by 3. And let me give you the first row. What can the second row be? Tell me a possible second row here for this matrix to have rank 1. A possible second row is 2a10. The second row is a multiple of the first row. It's not independent. So tell me a basis for the, oh yeah, sorry to keep bringing up these same questions. After the quiz I'll stop. But for now, tell me a basis for the row space. A basis for the row space of that matrix is the first row, right? The first row, 1, 4, 5. A basis for the column space of this matrix is, what's the dimension of the column space? The dimension of the column space is also 1, right? Because it's also the rank. The dimension, you remember, the dimension of the column space equals the rank equals the dimension of the column space of the transpose, which is the row space of A. Okay, and in this case, it's 1. R is 1. And sure enough, all the other columns are multiples of that column. Now, there ought to be a nice way to see that, and here it is. I can write that matrix as its pivot column, 1, 2, times 1, 4, 5. A column times a row. 1 column times 1 row gives me a matrix, right? If I multiply a column by a row, that's 2 by 1 matrix times a 1 by 3 matrix. And the result of the multiplication is 2 by 3. And it comes out right. So what I wanted, my point is that rank 1 matrices, that every rank 1 matrix has the form some column times some row. So U is a column vector, V is a column vector, but I make it into a row by putting in V transpose. So that's the complete picture of rank 1 matrices. We'll be interested in rank 1 matrices. Later we'll find, their determinant, that'll be easy, their eigenvalues, that'll be interesting. Rank 1 matrices are like the building blocks for all matrices. And actually, maybe you can guess. And if I took any matrix, a 5 by 17 matrix of rank 4, then it seems pretty likely, and it's true, that I could break that 5 by 17 matrix down as a combination of rank 1 matrices. And probably how many of those would I need? If I have a 5 by 17 matrix of rank 4, I'll need 4 of them. 4 rank 1 matrices. So the rank 1 matrices are the building blocks. And out I can produce every every rank 4 matrix out of 4 rank 1 matrices. Okay, that brings me to a question, of course. Would the rank 4 matrices form a subspace? Let me take all 5 by 17 matrices and think about rank 4 the subset of rank 4 matrices. I'll write this down. You see, I'm reviewing for the quiz, actually, because I'm asking the kind of questions that are short enough, but that bring out, do you know what these words mean? So I take my matrix space N now is all 5 by 17 matrices. And now the question I ask is the subset of rank 4 matrices. Is that a subspace? If I add a matrix so if I multiply a matrix of rank 4 by a rank 4 or less, let's say, because I have to let the 0 matrix in if it's going to be a subspace. But that doesn't, just because the 0 matrix got in there doesn't mean I have a subspace. So the question really comes down to, if I add 2 rank 4 matrices, is the sum rank 4? What do you think? No, not usually. Not usually. If I add 2 rank 4 matrices, the sum is probably, what could I say about the sum? Well, actually, the rank could be 5. If it's a general fact, actually, that the rank of A plus B can't be more than rank of A plus the rank of B. So this would say if I added 2 of those, the rank couldn't be larger than 8, but I know actually the rank couldn't be as large as 8 anyway. How big could the rank be? For the rank of a matrix in M could be as large as 5. Right. So they're all sort of natural ideas. So rank 4 matrices, or rank 1 matrices, let me change that to rank 1. Let me take the subset of rank 1 matrices. Is that a vector space? If I add a rank 1 matrix to a rank 1 matrix? No, it's most likely going to have rank 2. So I'll just make that point. Not a subspace. Okay. Those are topics that I wanted to just fill out the previous lectures. I'll ask one more subspace question, a more likely example. Suppose I'm in, let me put this example on a new board. Suppose I'm in R4. So my typical vector in R4 has 4 components, V1, V2, V3, and V4. Suppose I take the subspace of vectors whose components add to 0. So I let S be all vectors V in 4-dimensional space with V1 plus V2 plus V3 plus V4 equals 0. So I just want to consider that bunch of vectors. Is it a subspace, first of all? It is a subspace. It is a subspace. How do we see that? It is a subspace. Formally, I should check. If I have one vector whose components add to 0, and I multiply that vector by 6, the components still add to 0, just 6 times 0. If I have a couple, a v and a w, and I add them, the components still add to 0. Okay, it's a subspace. What's the dimension of that space, and what's the basis for that space? So you see how I can just describe a space, and we can ask for the dimension, as to the basis first, and the dimension. Of course, the dimension is the one that's easy to tell me in a single word. What's the dimension of our subspace S here? And the basis. Well, tell me some vectors in it. Well, I'm going to ask you again to guess the dimension. Again, I think I heard it. 3. The dimension is 3. Now, how does this connect to our AX equals 0? Is this the null space of something? Is that the null space of a matrix? And then we can look at the matrix and we know everything about those subspaces. This is the null space of what matrix? What's the matrix where the null space is then AB equals 0? So I want this equation to be AB equals 0. V is now the vector. And what's the matrix that we're seeing there? It's the matrix of 4, 1. You see that if I look at A, B equals 0, for this matrix A, I multiply by B, and I get this requirement that the components add to 0. So I'm really, when I speak about S, I'm speaking about the null space of that matrix. Okay, let's just say we've got a matrix now. We want its null space. Well, tell me its rank first. The rank of that matrix is 1, thanks. So R is 1. What's the general formula for the dimension of the null space? The dimension of the null space of a matrix is, in general, an m by n matrix of rank R. How many independent guys in the null space? N minus R, right? N minus R. In this case, n is 4. 4 columns. The rank is 1, so the null space is 3-dimensional. So, of course, you could see it in this case, but you can also see it here in our systematic way of dealing with the 4 fundamental subspaces of a matrix. So what are all 4 subspaces then? The row space is clear. The row space is in R4. Yeah, can we take the 4 fundamental subspaces of this matrix? Let's just kill this example. The row space is 1-dimensional. It's all multiples of that row. The null space is 3-dimensional. Oh, you better give me a basis for the null space. So what's the basis for the null space? The special solution. To find the special solutions, I look for the free variables. The free variables here are, there's the pivot. The free variables are 2, 3, and 4. So the basis for S will be, I'm expecting three vectors, three special solutions. I give the value 1 to that free variable. And what's the pivot variable if this is going to be a vector in S? -1. Now the rows add to 0. The entries add to 0. The second special solution has a 1 in the second free variable, and again a -1 makes it right. The third one has a 1 in the third free variable, and again a -1 makes it right. That's my answer. That's the answer I would be looking for. A basis for the subspace S, you would just list three vectors, and those would be the natural three to list. Not the only possible three, but those are the special three. Okay, tell me about the column space. What's the column space of this matrix, A? So the column space is a subspace of R1, because n is only 1. The columns only have one component. So the column space of S, the column space of A, is somewhere in the space R1, because we only have, these columns are short. And what is the column space actually? It's just talking with these words is what I'm doing. The column space for that matrix is R1. The column space for that matrix is all multiples of that column. And all multiples give you all of R1. And what's the remaining fourth space? The null space of A transpose is what? So we transpose A. We look for combinations of the columns now that give 0 for A transpose, and there aren't any. The only combination of these rows to give the 0 row is the 0 combination. Okay. So let's just check dimensions. The null space has dimension 3. The row space has dimension 1. 3 plus 1 is 4. The column space has dimension 1. And what's the dimension of this, like, smallest possible space? What's the dimension of the 0 space? It's a subspace. 0. What else could it be? I mean, we have to take a reasonable answer, and the only reasonable answer is 0. So 1 plus 0 gives, this was n, the number of columns, and this is m, the number of rows. And let me just say again then, the subspace that has only that one point, that point is 0-dimensional, of course. And the basis is empty, because if the dimension is 0, there shouldn't be anybody in the basis. So the basis of that smallest subspace is the empty set, and the number of members in the empty set is 0, so that's the dimension. Okay. Good. Now, I have just 5 minutes to tell you about, well, actually about this is now this last topic of small world graphs, and leads into a lecture about graphs and linear algebra. But let me tell you, in these last minutes, the graph that I'm interested in. It's the graph where, so what is a graph? Better tell you that first. Okay, what's a graph? Okay, this isn't calculus. I'm not thinking of like some sine curve. The word graph is used in a completely different way. It's a set of a bunch of nodes and edges. Edges connecting the nodes. So I have nodes like 5 nodes, and edges, I'll put in some edges. I could include them all. Well, let me put in a couple more. There's a graph with 5 nodes and 1, 2, 3, 4, 5, 6 edges. And some 5 by 6 matrix is going to tell us everything about that graph. Let me leave that matrix the next time and tell you about the question I'm interested in. Suppose the graph isn't doesn't have just 5 nodes, but suppose every person in this room is a node. And suppose there's an edge between 2 nodes if those 2 people are friends. So have I described the graph? It's a pretty big graph, 100 nodes, and I don't know how many edges are in there. There's an edge if you're friends. So that's the graph for this class. A similar graph you could take for the whole country. So 260 million nodes and edges between friends. And the question for that graph is, how many steps does it take to get from anybody to anybody? What 2 people are furthest apart in this friendship graph, say for the U.S.? By furthest apart, I mean the distance from, well, I'll tell you my distance to Clinton. It's 2. I happen to go to college with somebody who knows Clinton. I don't know. So my distance to Clinton is not 1, because I don't, happily or not, don't know him. But I know somebody who does. He's a senator, and so I presume he knows him. Okay, I don't know what's your distance to Clinton? Well, not more than 3, right. Actually, true. You know me. I take credit for reducing your Clinton distance. What's your distance to Monica? Anybody below 4 is in trouble here, or maybe 3, but right. So, what's Hillary's distance to Monica? I don't think we better put that on the tape here. It's 1 or 2, I guess. Is that right? I don't. Well, we won't think more about that. So, actually, the real question is, what are large distances? How far apart could people be separated? And roughly, this number 6 degrees of separation has kind of appeared. It's a movie title, it's a book title, and it's with this meaning that roughly speaking, 6 might be a fairly, not too many people. If you sit next to somebody on an airplane, you get talking to them. You begin to discuss mutual friends to sort of find out, okay, what connections do you have? And very often you'll find you're connected in like 2 or 3 or 4 sets. And you remark it's a small world, and that's how this expression, small world, came up. But 6, I don't know if you could find, if it took 6, I don't know if you would successfully discover those 6 in an airplane conversation. But here's the math question, and I'll leave it for lecture 12, and do a lot of linear algebra in lecture 12. But the interesting point is that with a few shortcuts, the distances come down dramatically. I mean, all your distances to Clinton immediately drop to 3 by taking linear algebra. That's like an extra bonus for taking linear algebra. And to understand mathematically what it is about these graphs, or like the graphs of the World Wide Web. There's a fantastic graph. So many people would like to understand and model the web. What are where the edges are links and the nodes are sites, websites. I'll leave you with that graph. And I'll see you. Have a good weekend and see you on Monday.